next speaker will be Dominique Meyer. So he did his PhD, his Bachelor of Science in Physics at the University of California in San Diego in 2017. And is actually now a PhD student in the Department of Computer Science Engineering, working with Professor Küster and Christensen together. He's part of the Contextual Robotics Institute and focuses on the development of imaging systems for autonomous ground and aerial vehicles, so a hot topic. As National Geographic Young Explorer, he has led numerous expeditions to digitally document at-risk cultural heritage sites around the world and is continuously passionate at applying vision systems for large-scale mapping. So we're very much looking forward to this talk now about StarCam. So let us welcome Dominique, please.
Thank you, everyone. Thank you for the introduction. It's a privilege to be here and talking to you about a project I have the privilege of having been working with. A big shout out to Daniel Sandin and the audience for having led the project over the last 2 years, Greg Dahl for having initiated the mechanical design and the display systems, which we'll talk about, and also importantly, Harlan Baker, who has actually been the original inventor of this design and who holds a patent for the interleaved stereoscopic camera. So over my talk, I'll be going a little bit about the background of different stereoscopic 366 systems that are available on the market, the design motivation between having high resolution cameras of such, and then addressing the main difference between a radial spoke design and an interleaved parallel design. So if you're a little confused about what these words mean, I'll get to those shortly. We're going to explore some synthetic stitches of these two results from the cameras to see how they compare, discuss their performance differences, and introduce the physical camera, the StarCam as we call it, and its real-world capture data. So, as you will probably have heard about, there have been a large number of 360 stereoscopic cameras on the market over the last years, pronouncedly the Facebook 360 camera on the left, the Insta360 views. And as you see, there's some differences in their designs. Some are radial, some are parallel. They have different resolutions outputs, and some use many more cameras than others. Why is that? So here I've kind of summarized these in a table, and as you see, there's a really huge difference. We're trying to understand why are some parallel, why are some radial, and which conditions make it better in one compared to another. Our camera, which we're proposing, is actually much higher resolution than even the Facebook camera, but we are only talking 30 frames per second at the mode we're driving it. So until now, head-mounted display systems have really not needed the higher resolution as we've already had. You know, a 4K input video, it looks pretty decent in a head-mounted display. And going up to 18 megapixels per eye, you know, we're starting to drive the requirement for higher resolution. At the University of California of San Diego, which I'm at, I've had the privilege of working with display systems and visualization spaces that actually have the resolution, right? So on the right, as Dan mentioned, is the Sun Cave, and that's a recent construction of a fully enclosed stereoscopic system, which Greg was the designer of. And that's really where we needed the data to be able to visualize it. We're talking 500 megapixels of resolution in displays right there. What data do we have nowadays that can do 500 megapixels at 30 frames per second? Not very much. So previously, we've been working with the Cave Cam. The Cave Cam is a stereoscopic camera that's pivoted on a gimbal around the center of the two camera optical centers in the middle. So this is actually a tele version of it, and as you can see, the optical center in the lens is about there, and the center about which it's rotated is between the cameras. And that works pretty great because we can rotate about that point. But when we want to build a video system, we need to be able to have more cameras, and therefore we need to offset them away from that rotation point. So this is the introduction to the difference between the interleaved parallel design and the radial spoke design. On the left, you see that we have stereo pairs, the blue cameras, the orange cameras, and the green cameras, which are parallel. right? And as you can see here, they're pretty much at interocular distance close to what humans have. On the right, we've got a radial design, which has been widely used in industry. But the main difference is that the overall system size is much bigger of the radial because you commonly offset these cameras along the radius or the circumference of the circle by about the interocular distance or the stereo baseline of 75 millimeters. So we will address two camera designs. The StarCam, which we have both the synthetic and the real-world camera design of, and the SPOCAM, which we only rendered in synthetic data. As you can see, they both have the same stereo baseline of 75 millimeters, but the big difference is that the StarCam has a much smaller overall system diameter compared to the SPOCAM. Some CAD renderings of these two designs. So our hypothesis going into this research topic was we think that the parallel interleave design is going to have much better stereo performance. Because we have the two cameras being parallel, we need to do less reprojection, as you can see, as compared to the radial design, as you can see up here, therefore not lose resolution as much and have much bigger overlap. Therefore get better depth estimations from the two cameras. It is, however, suggested in a few literature papers that the panoramic stitching would be slightly less good, which is why many people use the radial or stroke design, such as the Make a Stereo paper and the Facebook system. The disadvantage of the radial design, however, is that it does require an overall system that is much larger. If I go to say for the parallel interleaved, we did really require very small cameras to be able to interleave them in the way we did. For slightly bigger cameras, you have to offset them, and again, you get a slightly larger system diameter. So we did some tests where we generated 16 cameras from a 3D scene in computer graphics with a walking man. The walking man was set at 2-meter walking distance radius around the camera and a 3-meter distance. So we wanted to see whether the distance had an effect on the quality of stitching. So these are two example stitches from the sequences you'll see. The only difference we have with the synthetic data of the StarCam compared to the real data is that we increase the vertical field of view slightly more. In the real camera, we have 45 degrees vertical. In the synthetic, we actually increased it over to 60, so we have slightly more vertical degrees of the field of view. The input resolution is the same, and you will see that because of the reprojection, so going back a few slides where we're seeing that the parallel has more overlap, that results that the SPOCAM has slightly more cropped on the vertical axis. So we went in trying to use some of the more standard stitching comparisons, so looking at how the features are consistent between stitch panoramas, both in monocular stitches and binocular stitches. So when you have a feature identified over the two images, how do they offset when intersecting? We've got certain areas in the images that are seen by 4 cameras and others that are seen by 2 cameras. So when we consider the cases by 4 cameras, we can come up with an error rate. What we determined is that these units, which are in pixels, are actually pretty small. So statistically speaking, we're around a pixel consistency, which with the standard deviation of nearly also a pixel means that the statistical significance of this data is not very much. We see that the StarCam performs slightly better than the SPOCAM in these comparisons, but not statistically much. When we consider the depth from both camera systems, we're able to identify a depth estimate, so distance to a feature in 3D space because of the stereo vision. And that gives us an interesting metric of how the geometric properties work of these cameras. We were expecting the StarCam to do slightly better, but it actually did slightly worse. Also the last slide and this slide, these are error measurements, so the lower the better. But again, because of the large standard deviation, these are not very significant. There we go, both should be playing now. So this is now an example stitch of the StarCam, and as you can see, the walking man seems to be stitching pretty well, right? And you can see them walking across the seam, and it looks pretty good. On the spoke cam, we also have the same situation, except that you might see a little bit more stitching errors. So with the technique we used to stitch these two panoramas, we used an energy map, which is derived mainly from the depth map, to indicate different areas at different distances and do a patch-based system to do the approximate stitching. And with this approach, we did see that there were some failures across these stitches. As you can see, the roof in the background appears in the foreground before the walking man, and in the spoke cam, the even more confusing one, the face is kind of more distorted. So these are the kind of stitching errors which we're looking at. Another frame where this is significant is the back. But here we see that the StarCam stitched it perfectly well. So we did some statistics over the two courses of these video sequences and found that the StarCam had a slightly better overall stitching quality with less seams. Now, this method was mainly based on normal panoramic stitching, so we're doing a feature-based reprojection to minimize the error. But we can also look at the depth estimation and do a full scene reconstruction. So this is where we're reprojecting 3D point clouds into 3D space and seeing how good these look. And as you can see, the point cloud from a top-down view of this world is not very great, but when you look at it from the perspective of the camera, it actually works out to be pretty great. So really thinking about how we can do pretty decent depth estimate from the perspective of the camera, but not great of the whole environment. Moving the camera around and applying multi-view geometry techniques would result in much better results. So now with the real-world camera, a few years ago, Greg and the team started working with the Raspberry Pi camera. So at the time, this was a small cell phone camera that was one of the most smallest packaged sensors at a decent price with a supposedly good interface, the Raspberry Pi. It turned out that these cameras did not synchronize well, and that was kind of a showstopper because we needed the rolling shutter of these cameras to be synchronized to the best of our ability to guarantee the stitching, and that not being able to be met by these cameras, that design was abandoned, and we moved to the slightly newer version, which is called the StarCam. In this design, we used C3 cam cameras. So these cameras also use cell phone sensors. It's the AR1335. And that sensor can be driven at 60 hertz with 1080p and 30 frames per second at 4K. It does have a full 13 megapixel mode, which we are not exploring much, but it does do that. For the experiments we have done so far, we've been primarily driving it at 30 frames per second 1080p, though we could drive it more in the future. It does have on-camera compression, which is very nice, so that we don't have to deal with raw images, but we can get the raw images should we want them. And what's most interesting is that they come with a chip which actually converts the MIPI interface on the camera to a standard USB camera, so it's practically a webcam when you plug it in. The downside to that is that you have to use V4L and DirectShow. And if you've explored that domain much, you will see that this is a little bit of a headache and causes many issues to guarantee timing and not losing frames along the way. So this camera design has a stereo baseline of 75 millimeters, so that's slightly big head in compared to the human stereo baseline. But what's nice is that this whole camera fits into this little case. Please come to the demo later today, where we're going to showcase the camera and have some 360 videos to show you. The capture system relies on having two computers where each of the 8 cameras go into. We initially started with that because we were dealing with so much data, right? So when we're pulling raw images at 30 frames per second from each camera, we were saturating USB 3 host controllers with each camera. Transitioning to onboard compression allowed us to have 2 cameras per USB host controller, but that still required many, many PCIe cards, which is why we distributed it over the system. We now transitioned to a much smaller single computer system where we're able to fit a 1080 Ti and 5 USB 3 host controller cards, each with 4 USB host controllers, to make the system more portable. So you can see the StarCam with the real-time feed of the cameras and the computer that drives the whole system. So on that, we're capturing and writing to an NVMe to make sure that no frames are lost along the way. So as I mentioned, having correct synchronization to the rolling shutter was crucial. So these cameras were a little unique that we're able to actually do that with some experimentation and actually electronically trigger the cameras so that every readout of pixel row along all 16 cameras was perfectly synchronized. So to the evaluation of what actual acuity or resolving power of these cameras were, we did a eye chart test, which served actually pretty well. On the left, you've got the standard eye chart, medical eye chart, which has a few letters scaled to the appropriate size so that when read at 10 feet, you'd be able to determine the acuity of the system. So we tested the system with this eye chart at 1080p, 4K, and 13 megapixels to see how the resolving power changed. And at 1080p, we're looking at 2040 vision, so that's slightly worse than standard human vision, but is still enough to pass your California driver's license. 4K is about 2020, which is about human resolving power. And that's the first time we're actually approaching full human resolving power over a panoramic system in stereoscopic view. So that's what kind of makes this camera unique, is that we're achieving this resolving power over this spherical capture. So here is an example of this camera stitch in motion outdoors. As you can see, all 16 cameras have been stitched decently well. You can still see some seams as they're crossing, people are about 1 meter from the camera. But in the background, everything stitches well, and the colors are consistent. So we're doing a lot of work in making sure that all cameras are perfectly synchronized in terms of exposure, gain, and focus. We've also done a little bit of testing on autonomous vehicles to see whether we can capture scenes while driving it around. So we strapped it to our autonomous vehicle on campus and drove it around, and the results look something like this. Or not. I'll show you this after at the demo. But this is actually a great example to show that these sensors are not the best in high dynamic range scenes. So with the sun glare coming out, this actually saturates the pixels and makes them very usable. But we're looking at different sensors in the future that allow us to have better dynamic range. So now to the future works. The big problem we have is that we're still not stitching the data in real time. To do that, we're going to have to heavily hardware accelerate this process. So this is a very computationally expensive task. We can be using GPUs or FPGAs to do so, and that's part of my work coming up in the future, to see how we can actually leverage FPGAs to do real-time stereoscopic stitching and coincide those over different stereo pairs. And then also importantly, look at how do we increase that vertical field of view from 45 degrees over to full 180 degrees. So that's upcoming works. I want to thank everyone on the project that have made this possible, the NSF for funding the Sensei project, Harlem for your support, Daniel for all your great advising and experience on this project, Greg for starting it, and everyone else to make the software happen. Thank you very much.